Now, in this article, kinematics of circular motion, uh, we are going to learn uniform circular motion and non-uniform circular motion. In uniform circular motion, we have seen in previous lecture how the direction of the angular velocity is there and how we can find by the right hand thumb rule the direction of the angular velocity, and also the terms which are constant and how the each value is find, and the relation of between the terms, and radial acceleration also. And in UCM the time period was the time period was 2 pi n. Okay, okay, the time period was 2 pi n, which is equal to, where n is the frequency, and we know n is equal to, where what is n is equal to, we have already learned n is equal to 1 upon t. Then after substituting it, n, the value of n in this equation, what we will get, 2 pi upon t. So n is the frequency, t is the time period, and 2 pi is this, and this was the in UCM. In previous lecture we have studied that in UCM. Now we will see what is the relation between the angular velocity and linear velocity. Okay, in vector form, uh, what is v is equal to omega cross r in vector form, and in magnitude form we already know v is equal to r omega. Okay, from this we we can also write as uh, find the value of omega is equal to v upon r, and radius also r is equal to v upon r. If the question is asked in your exam, you can solve the problems by using these equations, where v is the tangential velocity and omega is the angular velocity and r is the radius of the circle. Now further we will see what is the relation between the angular velocity and the acceleration. Okay, previously we have seen what is the relation between the angular velocity and linear velocity. Now we will see what is the relation between the angular velocity and acceleration. We know what is the value of acceleration. A is equal to minus omega square r. Okay, in this is in a vector form, and in magnitude we can write as, in the form of magnitude we can write this as a is equal to omega square r, and also we know the relation, uh, what is the relation, v omega is equal to v upon r. We will substitute this v omega is equal to v upon r in this equation. What we will get, v square upon r square, and this r as it is. Okay, then this r square and this r, which will get, it will get cancelled. We will get v square upon r. Okay, and again we know the relation, r is equal to v upon omega. Okay, r is equal to v upon omega. Now we will substitute the value of r in this equation. What we will get, v square upon v upon omega. Okay, then further it will be v omega. Then acceleration, now the value is A is equal to V omega. So in exam when the question will be asked, you can solve this by these formulas. Now further we will see non-uniform circular motion. What is non-uniform circular motion? Now we are going to see what is non-uniform circular motion. Previously we have seen the relation between the angular velocity and acceleration and uniform circular motion. Okay, and now we will see the non-uniform circular motion. In non-uniform circular motion, the speed is not constant, the velocity is also not constant, and angular acceleration is also not constant, and only the omega is constant, and d omega by dt is not equal to 0. And consider the example of the fan. When the fan is on, what happens when the uh, before switching on the fan, it was at rest. Okay, then after getting switch on, it takes its speed slowly. While taking the speed, it increases its speed, and after some time it takes a constant speed and moves in uniform circular motion. At that time, it is in uniform circular motion. But while taking the speed, it was in a non-uniform circular motion. Again, we off the switch on, the first we have switch on, then after that we have switch off the fan. Again, the speed of the fan decreases, goes on decreases. And when again we switch on the fan, means we have to study that when it is in uniform circular motion and when it is in non-uniform circular motion, and what is how it is the how the direction of the angular velocity and angular acceleration is find. After this, we will see that also in a diagrammatic form. Now we will see this how when it takes the speed, when it is switched on, it speeds. It is in non-uniform circular motion. In non-uniform circular motion, there is a radial acceleration also and tangential acceleration also. Okay, and when it stops, then also it is in non-uniform circular motion. Means when it gets starts slowly, it gets this. It takes the speed slowly, slowly. It get on, and after we switch off it slowly, it is stopping. Okay, means there is a change in the speed of the uh, particles of the all the particles of the fan. Okay, means the particle, each and every particles of the fan which are situated, they are moving in a non-uniform circular motion, and in this both of the between, when it is switched on while taking the constant speed, it is in non-uniform circular motion, and between that it is moving in uniform circular motion, means in a constant speed. At that time it is in circular uniform circular motion. Okay, and when it is getting switched off, the it is in the fan is in the non-uniform circular motion, and the direction of the angular velocity and angular acceleration is also opposite. Okay, how? But the um, uh, directions are opposite. We will see further. Now we have to see this. The magnitude of tangential velocity changes corresponding when the magnitude of the and tangential velocity changes, the corresponding omega also changes. Why? Because alpha is equal to d omega by dt. Okay, means the tangential velocity. As we seen in the previous lecture, how the tangential velocity is moving with the particle in a tangential form. It is any time at any time you can see that it is always tangential to the circle. It will not change its position. Whenever it will go in direction upwards or downwards, it will remain tangential only. So the magnitude, when the magnitude of the tangential velocity is changing, the corresponding angular velocity will also change because omega is alpha angular acceleration alpha is equal to d omega by dt. Okay. And what is tangential acceleration? The acceleration responsible for the magnitude of the velocity is directed along or opposite to the velocity. Means the acceleration responsible for the magnitude of the velocity is directed along or opposite to the velocity. Hence, always it is tangential. So this is called as the tangential acceleration and it is denoted as a suffix t. So this is the tangential acceleration. Okay, and now we will see how the uh, fan, taking the example of a fan, how we can find the direction of the uh, angular velocity and angular acceleration. Consider this is a fan. Okay. Here it is the, as we know, already know, when the particle is moving in this direction by the right hand thumb rule, previously we have seen already. So the direction of the angular velocity omega is in the upward direction with the thumb outstretched. Okay, when it is increasing its speed, when it is switch on, okay, increasing, and with that the direction of the angular acceleration also in the same direction. Means when the fan is get, when we switch on the fan, as the angular acceleration changes in the direction of this, the direction of the angular velocity in this direction, the same direction is the angular acceleration also. But in the case of the fan, when it is get off, okay, it is moving in this direction, the direction get opposite. Okay, so this is the direction of the angular acceleration when the fan is off, switch off, and it is decreasing here. Here the angular velocity, you can see that it is in the upward direction. Angular velocity is in upward direction and angular acceleration is in the downward direction. Means when the fan is switched on, the direction of the angular velocity and angular acceleration is same. Sorry. And when the fan is getting off, okay, here you can see the direction of the angular acceleration and angular velocity changes. It gets opposite. You can see that. Now we will see what are the dynamics of the circular motion. Now we have completed what is kinematics of circular motion, that is uniform circular motion and non-uniform circular motion. Now we will see what are the dynamics of circular motion. Okay, in that first is centripetal force. We know very well what is centripetal force. The centripetal force is a force, the particle which is moving along the circumference of a circle and it is directed towards the center. Okay, so consider this is a circle with a radius r and this is the one point. Suppose this is the consider the point here along the circumference of the circle. Okay, and the direction is, this is the particle, here it is moving round and round along the circumference of the circle and it is directed towards the center. Means the acceleration is responsible the acceleration is responsible for the circular motion. If there is no acceleration, there will be no circular motion. Okay, and we we have also previously seen that, what we have seen that the radial acceleration or centripetal acceleration. I have said that you may be remembering that while calculating the value of acceleration, okay, in uniform circular motion, I have said that radial acceleration or centripetal acceleration. So here it is written as A of r, means radial acceleration. Centripetal force or centripetal acceleration. Centripetal acceleration or centripetal or radial acceleration. So the centripetal force is, this is the centripetal force which is denoted as C of F sometimes, CF centripetal CP, sometimes it is denoted as CP also. Now there's now the radial acceleration is in the vector form, we know minus omega square r. We know, we have already seen A of radial acceleration is minus of omega square r. In the vector form, in the magnitude form, it is omega square r. Then after substituting the value of omega, what is the value of omega? We know from the relation that v omega is equal to v upon r. After substituting this, we have gotten the equation also, that also we have seen. Now this is also called as the centripetal force, as F is equal to, we know by the Newton's second law, what is Newton's second law, it is F is equal to ma. Here we will take as m F is equal to ma. In that case, here it is radial acceleration, we will take it, and substituting the value while finding the centripetal force. Here F is equal to centripetal force. F is equal to m into m, as it is substituting the value of a, radial acceleration here, what it is, minus omega square r here. Then here further these steps are substituting this value here, m of a r, F is equal to m a, radial acceleration here, substituting this value in this equation. Then omega square r, what we will do, we will take as F is equal to, what was the equation, F is equal to m into omega square r. Okay, here minus omega square r, here it is minus omega square r. Then substituting the value of omega, as usual, b is equal b upon r. Then what it will become, m as it is, here it will be b square upon this, b square upon r square. Okay, and this r as it is, this r and this r gets cancelled, and we will get as minus of mv square upon r. Okay, or in the magnitude form we can also write as mv square upon r, means the force is, we have provided, now we have got it, what is the force, which is mv square upon r. This is the radial force or centripetal force. The force is this. Now we will see what is centrifugal force.